Welcome to IglooConf, and let's have a great shout out to Alan. Welcome.
Excellent, and thank you to everybody who's been involved with this event, putting this event together. I don't know if I've been to every IglooConf. I've certainly been to quite a lot of them. And it's always been one of the best experiences of the year, one of the best conferences of the year in terms of the location, the audience, the presenters, and everything. It's always been really good. And it's great to be back here after a couple of years of sitting at home in a small box room doing presentations in different locations, but never really leaving my house. So a bit about the session. I'm going to be talking about neural networks. I'm going to be talking about basically starting out with what a neuron is, and then getting into image classification, custom vision, and rounding off looking at generative AI. Some of the things like DALL-E 2 and GPT-3 and Pix-to-Pix, those types of ways that you can actually generate stuff. That is not me dancing. It looks like me dancing, but the images are actually generated by a neural network based on the poses of Bruno Mars. So it's actually Bruno Mars movements, but that's AI generated. And hopefully you'll get an understanding of how that works by the end of the session. So there's an obligatory photo that I think somebody's got to take a picture of. Thumbs up when it's done. Okay. Excellent, thank you. So a bit about myself, Alan Smith. I work in Stockholm, just over the water, and I work at a company called Active Solution. We develop solutions for companies based on Microsoft Azure technologies, or mostly based on Microsoft Azure technologies. We're always looking for what's going to be the next big thing. We took a very early adoption of Microsoft Azure and persuaded many of our customers to start looking and considering using cloud computing. We're now focusing on Microsoft's AI offering, and we see, as you've seen in the previous session, there's great stuff that we can do with AI on the Microsoft platform, and also beyond the Microsoft platform, taking other frameworks and being able to run them within Azure ML and train models and so on. I was kind of thinking, AI, you can take a very serious theory-based approach with lots of PowerPoint slides and formulas, or we can have a cool, fun session with lots of demos. So I kind of think we're going to be taking the red pill. It's last thing on a Friday, so we can have some fun. So this popped up on my YouTube feed a couple of years ago. And it just really impressed me about how they can basically create this type of AI. I can actually drop to the YouTube video, and what they're doing is they're basically starting with a professional dancer, and they're basically sampling the pose from a professional dancer. So that's the source subject, who is a professional dancer. You then have a target subject that you can actually perform the movement mapping to. And what they're doing is they're basically detecting the pose of the professional dancer. Initially, I thought this was done using a Kinect sensor. However, there's actually a neural network called OpenPose, where you can basically send it a video or photos, and it basically detects pose within the actual photo and gives you out the actual positions, which can then be converted to an image. So the detected pose from the professional dancer is basically mapped to the source subject. So the source subject is going to theoretically, copy the moves of the professional dancer. And it really blew me away, sort of how they can, create this type of AI. And I thought, this is what people are doing at UC Berkeley. There's no way that I could do something like that. It's got to involve lots of data science and a real deep understanding of neural networks. However, their code is available on GitHub. You can download it. If you have a sufficiently large GPU, and you need quite a big one, you can actually get it running and train your own models. So I'm going to go through some of those. This is my favorite one they've done with it, with a ballet dancer. You can see that on both of those source subjects, they're capturing even the reflections behind the dancer are being captured. So how do we get there from knowing nothing about neural networks? We can start to think about, what a neural network is. And probably the simplest thing we can do in machine learning is something called linear regression. We've got this in Excel. We can, put our sales figures on Excel. We get a bunch of points on the graph, and we can just say, OK, let's draw a line that's going to be an approximation of that. And the way that we can find the optimal line is basically by moving the line around and calculating the minimum amount of loss. Those purple arrows are kind of representing the loss that we've got within that particular algorithm. And that's what's basically done within a single neuron. If we have a single input and a single output, we've got two parameters that we can specify on that neuron. The first one is the weight, and the second one is the bias. So if we take the input and multiply it by the weight, and then we add on the bias, that's going to give us the result, which is basically y equals mx plus c. It's the formula for a straight line. So that can basically do a linear regression with basically one neuron in a neural network. So to show how that works, I'm actually using PyTorch, and I've built a neural network, and it's doing apartment price prediction using linear regression. So if we just zoom in on the code, should be able to find the actual network. So this is the network that I have created in PyTorch. So I'm specifying it's only got one layer and it's only got one neuron. And that's basically the simplest network we can run. What I'm doing is I'm training it on apartment data. So what I'm feeding in is the price of an apartment and the area of an apartment in square meters. First thing we do is normalize the data, because neural networks don't like really big numbers. They typically like to work with numbers around about +1 to -1. And then we're able to train the model. So it takes a few seconds just to train that on the GPU. And you can see the actual results there of the training loss and the validation loss. I kind of should have stopped after about 25 epochs. You can see that the validation loss is increasing, and I'm overfitting quite a bit. But this is basically now got a trained model to predict the price of apartments. So if my apartment is 50 square meters, it's saying it's going to cost 3.2 million krona, about 300,000 euros. If it's 150 square meters, it's giving that prediction of 8.2 million krona. Interestingly, it's not just a price per square meter. If I put in a price of 0, 671,000 krona. So it is basically a constant and then just basically adding on something per square meter to that particular price. That's what the model found was being the best fit. So that's basically the simplest thing we can do with neural networks. Another way of representing data, how does it deal with the street name? The street name is also going to affect the price. You can't put words into a neural network, you have to convert them into numbers. So they have this thing called one-hot encoding, where you give the value of the street that this apartment is on, the value of 1. Everything else has a value of 0. And feeding that into a neural network, the weights can be trained to say that, well, an apartment on Svartvikslingen is going to cost, 1.2 times the average price, whereas an apartment on Vindvägen is going to cost 0.8 times the price. And just that calculation is then going to say, based on what street you're on, it can basically adjust that. And the neural network is going to be trained with those particular values. So this is a 7-segment LED display, or LCD display. What you could do is you could build a neural network, you could actually write code that could basically understand what type of figure that is. Fairly easy. If A and not B, and C and D and E and F and G, then the number is going to be 6. And what we're doing here is we're making binary decisions. We're dealing with logic, we're dealing with ands, and we're dealing with true and false. So going into neural network and machine learning, we kind of have to unlearn the concept that we're dealing with true and false. We're not dealing with true and false anymore. We're basically dealing with zeros, with numbers between, say, -1 and +1, or between 0 and 1. So, supposing the LED display is a few years old and it's starting to look like this, what number is this representing? So using a neural network, what we can do is we can take the actual values between 0 and 1 of the kind of a percentage of light that we're emitting from each segment, and we can basically use a neural network to be able to train it and make a prediction. So in this example, I just basically put in the numbers myself, but it may predict that there's a 50% chance of this being a 6, 40% that it could be a 5, and a 10% chance of it being an 8, sort of based on what the actual values are. So the next thing about neural networks, they're not going to give you a definitive answer. You show it a photo of a cat, and it will say it's 86% certain that this photo is a cat. You're going to be getting a numeric number coming out of it. So the neurons can have multiple inputs. So you can basically feed in, the 7 segments of a 7-segment LED display, and you can get it to basically predict, whether it's going to be a 2 or not, or whether it's going to be a 3 or not. And then you can imagine, going back to, say, the VIC-20 or the Commodore 64 or the ZX81 that you learned to program on if you're as old as me. And we had these 8x8 characters. You could build logic for that. And then you get into things like handwritten digits, whereby the pixels are a bit blurred. This thing is handwritten. And there's going to be maybe sort of 28 by 28 pixels here. So it does become a bit complex. How would you write code to be able to understand that that is a 9? And this is when neural networks come in. There's basically two data sets that you start using when you're working with custom vision solutions. They're these MNIST data sets. One of them is on handwritten digits, and the other is the fashion data set, which is basically 10 different categories of clothes. So you can actually train a regular neural network with these input layers, one kind of input for every pixel on that image. I haven't shown all of them there. And then we've got a number of hidden layers, and then you've got the predictor of what type it is. When you start out, the network is not going to be trained. So it's going to have no idea what this is. So you use labeled training data with maybe thousands and thousands of these images, thousands of T-shirts, thousands of dresses, thousands of shirts, and so on. And you basically train it. You know that this is going to be an ankle boot, and you use a progress called back propagation. And what you're doing here is you're setting the values for all of the biases and all of the weights within the neural network. So for this particular image, it's going to predict an ankle boot. Now, you can imagine that this is kind of okay. It does kind of work on these images. There is some visualization, actually, of how that works. It says demo, but I'm kind of cheating a bit. I'm just showing what this stuff looks like as it runs. And this is basically something called a multi-layer perceptron. I was thinking of writing code to do these animations myself, but some of the people on YouTube have done some fantastic animations. This is basically showing 2% of the actual connections on a neural network that is doing that prediction. And as the different pixels are firing, you can see it's making the predictions about what the actual figure should be. Now, you can imagine that this is okay if your images are going to be very, very clean. This is the actual Zalando website. This is where the data is taken from the MNIST fashion data set. So if your images are kind of like these ones of T-shirts, it's dead easy because they're always in the same place. It's going to be the same pixels that are represented when you're representing a T-shirt. However, if this is your image, how are you going to detect where the T-shirt is within that image? It's going to be in different positions. Even with, just go on here, sorry, I'm skipping back. Even with images like this, it's going to be quite challenging because all of these ones are occupying different pixels. So training a network on that, especially if it's like images of cats and dogs, not going to be possible with those linear networks. We need something a bit more complex because the kind of problems we're going to be solving in AI, there's some examples of them here. One of them is image classification, where you've got the whole photo, and is the whole photo a cat, or is the whole photo a dog, and making these multi-class predictions. The other one is object detection, where you show a photo of a cat and a dog, and it's going to identify the cat and give you a bounding box around the cat. Same thing with the dog, identifies the dog and gives you a bounding box around the dog. As you can imagine, object detection is a lot more challenging for a couple of reasons. Firstly, generating the data sets. Somebody has to draw the bounding boxes on tens of thousands of images. It's a slow and tedious process, also quite error prone in getting consistency on how accurate those boxes are. With the classification, it's a lot easier. You've just got to sort the images into folders. 10,000 images of cats, 10,000 images of dogs. You can generate that data very easily by Googling for cat in the image search and just basically saving the web page, which will save all of the images. And you've got 200 or 300 photos of cats, and that can be used in the training set. There's other things that you can do, like semantic segmentation. We've all seen this. We've been working in a Zoom meeting, and there's always one person in the Zoom meeting who has an amusing background. They're in prison or they're in a bar, and they haven't got a green screen. But what they're doing is they're using semantic segmentation within Zoom, and what it's doing is basically taking the pixels that represent a person and the pixels that are not a person. And the pixels that are not a person is just basically filling in with a prison cell or the inside of a bar. And that's why if somebody picks up a bottle of water, it's not sure whether this pixel is a person or whether this is going to be the background, and it does get a bit distorted. That's basically what semantic segmentation does. You can also do regression with vision. This was a popular website a few years ago, How Old Am I?, where you could basically upload a photo. And it is doing object detection. It's detecting that there is a face in the photo. But then we're getting a numeric value out of that face, which is going to be the age. And it's able to do this age prediction by taking, thousands and thousands of photos of people with different ages and labeling that data and training a neural network to be able to come out with the age prediction. So we need to think a bit higher level of complexity when we're working with these types of images. And this is when we get into convolutional neural networks. So this is basically a matrix, 5x5 matrix with different values shown by the color. And the process of convolution, you basically scan that matrix across the input image. And you can see that when the matrix gets to that position on the 1, it's going to give an output, because the pixels on the actual digit of the line going down start to match the pixels on the matrix. And this is what goes on inside convolutional neural networks. They look something like this. However, they tend to have a lot more layers and a lot more channels. We have our input, and then we've got these channels here. And when they talk about a 5x5 kernel, that's the actual size of the matrix that's being scanned across. Also, if it's a color image, you've basically got 3 color channels, red, green, and blue, and you'll have a 5x5x3 three-dimensional matrix that's scanning across there. And then you go into different layers. So you go into another layer, and then another layer, and another layer. And eventually, at the end, to classify what digit it is, you have a linear network, which is pretty much the same as we saw in the first animation. So when you're training these, nobody really fully understands exactly how these things work. But generally, things like edge detection and shape detection are done in the early layers of neural networks. Before we had neural networks, people who were building custom vision solutions would actually manually program matrices to be able to do things like edge detection and shape detection. It was all coded manually. Now it's just trained using networks. So we detect the edges, we can detect shapes, and then we can start to do a feature detection, and we can then do the actual classification. So looking at how these things work, there's a couple of good examples again on the YouTube animations. So this is basically showing the convolution process, how we're basically scanning this particular character and generating the first convolution layer. I'm going to whiz through because there's quite a few convolution layers that are being created as we go through. And as we get towards the end of the network, we're going to actually do the classification. And what that means is basically using a regular network to decide what type of figure that is. So here they're basically doing the matching and getting the percentage as to which character it is by stamping them out like that. However, in reality, when we start working with real-world custom vision solutions, the networks actually look something like this. There can be hundreds of layers. There can be thousands and thousands of these actual kernels, and millions and millions, sometimes billions, trillions of parameters within the neural network. So it can take a really long time to train these. You can see this is basically going through the first section of layers, and as we go through into more depth, every convolution layer is going to get more and more of these outputs. So these networks are really big, really challenging. They take a lot of memory, and they can take a long time to actually process and to tune. So in order to speed up the process, we can think about being able to optimize this. Another thing you can do with these images is music genre classification. I became interested in this watching a few things on YouTube channel. You've basically got a waveform. Music is a waveform. However, if you've worked with music and with music editing programs, if you're a musician, you will maybe understand that you can have this concept of a spectrogram. And what this is showing is frequency over time. So I think at the top they've got the bass frequencies, at the bottom it's the treble frequencies. And this spectrogram is produced by a mathematical formula called a fast Fourier transform. So various things like Audacity will be able to display spectrograms. So the spectrogram is basically an image which can be fed into a neural network, and it can actually do classification on what type of music it is. I was demoing this last week. I was actually training the network in Azure ML. I think it took about 15 minutes to train the network in Azure ML. It's a fairly quick process. And to test the actual results, what I did was I went to YouTube and found a video with different music genres. So what this is doing is basically using that PyTorch network to be able to detect the type of music. And what it's doing is it's using a 10-second sample. You can see it's not too great on predicting jazz here. And it's basically trained on 10 seconds music samples. So it basically scans through on the actual 10 seconds section of music, but it's getting hip hop there. Seems to be doing that. And then rock. There is no rock as a classification. However, it's picking up that this is metal, and that's going up to 100% there. So it seems to be doing pretty well with that one. Again, folk. There is no folk music classification here. So it's trying to guess and thinking, well, maybe this is a bit like country music. Bit of classical music coming in there. Soul music is not a genre, but it does classify that as disco, which seems to be fairly accurate. And it's pretty sure that that is disco. And then we've got EDM, which it classifies as pop music. I was quite impressed kind of how accurate that is. There's good scenarios like, cataloging music collections and so on, where you can actually go in and build a system. I also tested it with different genres of dance music. I went to YouTube and got 2 hours of techno and 2 hours of euphoric house music and 2 hours of drum and bass. And it was actually quite good at being able to classify different dance music genres based on those particular data sets. So the feature identification, what we're doing really is identifying things and then making a decision. Thinking about that 7-segment LED display, you've got logic there. If this segment is on and this segment, then it's going to be number 3 or number 4 or so on. And when it gets towards the end of the neural network, it's saying if there is an ear and an eye and a mouth and a nose, then it's going to be a dog. If there's a blueberry in a paper cup, then it's going to be a cupcake. However, you do get these kind of edge case images that do confuse the neural networks and get classified incorrectly. So in order to basically make things run faster when we're training the models, we can basically freeze certain layers within a convolutional neural network. So the edge detection and the shape detection, once this has been trained on a specific set of data, you can basically freeze this and say, okay, keep the edge detection, keep the shape detection, and we'll train the feature detection and the classification. And this means that instead of training all of the parameters in the neural network, we're training a section of parameters in the neural network, which means that it's going to be a lot faster to be able to train those particular models. You could even choose to do this. Only train the classification layer, keep everything else, edge detection, shape detection, and feature detection frozen. This is what they do. They do a fantastic job of in the Azure Custom Vision service. So if we drop back to the portal into Azure Custom Vision, these are a few of the projects that I have been working with. One of them is the birds classification. I didn't know this, but there is a bird which is called an Azure Jay and an Azure Tanaja. And this is basically what an Azure Jay looks like. I think it's from an Eastern European country, and we would, in the West, it's probably called a blue jay, and that's basically called an Azure Jay. I thought it was cool that you've got birds named after Azure. And we can do a quick test on this by going in and browsing to local files, and in the test section, we should be able to find the Azure Jay and take one of those. And the test has not been seen by the neural network, and it's coming out with a prediction there. 99.8% certain that it is an Azure Jay. We can also go and test it with an image that it has not been trained on. So if we go to the African oyster catcher, it doesn't know what one of those is. So it's predicting that it's an alpine coupe with a 78% certainty. However, we can train it for that particular bird if we want to. It's very easy to use this actual software. You don't actually have to know anything about neural networks. So what we can do is we can basically go to Add Images, and I can browse down, not to the test folder, but I'm going to go to the train folder, and then we can go into the, let's take the Abbott's Babbler. Have we got that one already? Oh, we've got that one already, so let's take the next one. And I've been using 100 of each image. We want to keep a balanced training set, so if I select 100 of these guys, and I'm going to copy the bird name here so I don't get it wrong. Let's open those. We drop that in as a label. It's going to upload these 100 files, and then we've got the option of training the network. So when we train the network, the quick training will usually take about 2 or 3 minutes to train the network. It's very fast. We can do advanced training if we want to, and we can dedicate a number of hours to it. So if you're using this on your project, just do the quick training first, and it will tell you in a few minutes if it's going to start giving accurate results. And you can increase that accuracy by setting a training budget of several hours if you'd like to. But I'm going to go on just the quick training and click on train. And that hopefully will be done by the end of the session. You can also do things like object detection and tracking. Just a quick demo of how that works. I've got a solution here which I can run, I think. This is something called YOLO 5. Again, it's available on GitHub, and you can just basically download this. It's also doing something called deep sort, and sort doesn't stand for sort as we would think of in sorting an array. It stands for something like simultaneous object real-time tracking or something like that. You can see it's detecting a person, and it's running in real time. It's detecting, hopefully, a water bottle. And it will hopefully just be able to detect these objects as they move around. So you could use this for counting how many people are walking through a certain store and being able to do tracking like that. I've got a very, very poor GPU on that machine. It runs reasonably fast, even just on a very, very basic GPU. So thinking about image classification, we've been seeing in the last session how Azure has these cognitive services, and computer vision is one of these cognitive services. And what computer vision can do is it can take in an image, it can tag that image, it can identify objects. It can also provide a description of that image, a group of people sitting at a table using a laptop. Now, generative AI is basically going to switch that thing round completely. And DALL-E 2 is the most impressive that we've got so far. So if you give it a sentence like teddy bears working on new AI research underwater with 1990s technology, what it's going to generate is this as the actual output image. The DALL-E 1 was generating kind of cartoonish images. These kind of almost look like they've been set up as a photo, very realistic. And imagine what DALL-E 3 is going to come out. Maybe it's going to be generate a movie of teddy bears working on AI research underwater with 1990s technology. There is a website available for DALL-E 2. However, you can't basically free type anything. You can basically do these selections and see samples of this. So teddy bears mixing sparkling chemicals as mad scientists in a steampunk style, or as digital art, or as a 1990s Saturday morning cartoon. And you can see there's several images that it's creating there. That is really impressive, that image generation technology. It's improving so quickly, these types of technologies. Another really cool thing that we've got is text generation. Can anybody tell what's wrong with that description, that speaker bio? I didn't write Azure in Action. There is no book called Azure in Practice. I searched on Amazon. But the rest of it's correct. I've been working with Microsoft technologies for over 20 years. I've been involved in the Microsoft Azure community and a technical expert and speaker, and I'm a regular speaker at conferences and user groups around Europe. The first part was written by me. The second part was generated by an AI, which is called GPT-3. And it basically, I fed it that particular section, and I says, can you just continue that speaker bio for me, please? And it's generated that. It is really awesome technology. It's being used in, I think Autopilot uses it, same type of technology to automatically generate code. So let's see what we can do with this. Yeah, that's the one with my speaker bio. We've seen that one. So if I'm going to submit a section on Cosmos DB, in this demo-intensive session, Alan will introduce and demonstrate the functionality of Azure Cosmos DB. And we can fire that in, and it's just going to continue in the same style and hopefully generate a session proposal for me. This session will cover the basics as to what Azure Cosmos DB is, why you should use it, differences between SQL and NoSQL databases, differences between Mongo and Cassandra, Azure Table Storage and Cosmos DB. The demo application will be a web application that will include a web API service. The API service will use Cosmos DB to provide CRUD functionality for the web application. Awesome. Yeah. And we can do it again, and it's random, so it will just generate different presentations for me. Yeah. Yeah. And you can just change the technology, and you can do fun stuff. Alan will set off. In this demo-intensive session, Alan will set off a number of very powerful fireworks. We'll find out. It's thinking about it. I've tested this before, actually, and the results are varied. Some of them are a bit rubbish. Some of them are some of them are hilarious. It has come up with some stuff. Oh, it's actually set a date and a cost for it. Age limit 16 plus, and a phone number. So yeah, I think it's just pulled some random text from a firework display, but it did come out with other stuff. That doesn't look too good. It came out with one where it said that Alan is a maths teacher in Manchester who's basically produced stunning firework and laser displays for the Pride Festival in Manchester, which I thought was pretty cool. Yeah. Yeah, let's submit that one. Awesome. Yeah, so I thought of some other stuff to do with it. One of them was to create a song in the style of AC/DC, but about coding in Azure. So I put in this actual intro here like that, and some of these kind of varied. This one got pushing left, pushing right. The teams are going to with me. We're going to build. We're going to push. We're going to deploy. We're going to do it right. Blah blah blah. This one came, Azure is cloud in my mind. Azure is cloud in my mind. One-way call from Azure. Make deployment work now. Make notification work now. There's another one as well. I can't see you. I can't hear you. You're the cloud that keeps me going. Azure, the cloud that keeps me going. And it's pretty good how it's able to kind of pick that it should be song lyrics. It has to think about it a while, and some of the results are a bit hit and miss, but you can try it several times and see. So this is free to register. You get a credit of so many dollars, and each time you make a call, depending on kind of how much text you're generating, it's consuming a tiny fraction of that. Microsoft has actually bought this from OpenAI, and it is coming in cognitive services very soon. So you will be able to use this kind of a generation to be able to generate concepts. They didn't want to release it to the open market because people could do evil things with it. Think about the amount of fake news that's coming out. Spamming Twitter with fake news reports about whatever you want as an automated process will be something that will be fairly easy to set up. I'm not going to fail. We're going to rock it all day. We're not going to fail. Is it mentioning Azure? Oh, because we're running in Azure, the cloud, where it's always sunny, no matter what the mother one says. Awesome. And it came out. I did drop on my slides a couple of other examples of GPT-2. It came out with that one there, just in case that didn't work. I kind of like this one. The cloud is the future, the cloud is the present, the cloud is everything and always will be. It's fun stuff. How much time have I got left? Oh, not much. So basically, I'm getting on to generative AI. We're going to kind of dial about, that is what they call SOTA, or state-of-the-art stuff. We're going to kind of dial back a bit and look at stuff that we can actually do on our local machines. Pix2Pix is basically doing kind of augmentation of images. So they've got several models that you can test online, and one of them is able to generate buildings from these types of boxes. So that isn't a photo of a building, it's a generated image from the actual building elements that we place on a picture. It's able to do aerial photos to a map. It's also able to do maps to aerial photos as well, using, imagine how much data you've got available on Bing Maps or Google Maps to be able to train the model to do stuff like that. Able to take labels and generate a street scene. Obviously, the gaming industry is going to be looking at being able to generate photorealistic graphics in games and so on. Black and white to color, day to night, edges to photo. And you can play around with this as well. You can download it and train your own models. But there is a website where we can experiment with how this works. So going up to the cats, that cat only has one eye because the image only has one eye. So I can draw another eye on the cat and click on process, and the cat should hopefully get another eye. My drawing skills are very limited here. So there are some random ones that you can basically see that the line drawings are generating cats. The cats one isn't too great. The handbags one is a bit, the boots one there. This is taken from like Amazon product images, able to take line drawings and convert them to photos. And then we've got the building one, where we can basically draw a wall. Oh, that is a wall. And then we can draw maybe a door and windows. Process. And it's able to generate something that kind of looks a bit like a building with those elements in those particular positions and so on. So Pix2Pix is actually used in the Everybody Dance Now application. And the way that they use it is to take this pose that is generated from the open pose and to be able to convert that through the Pix2Pix network into a person in the position of that pose. That's my son James, who very kindly volunteered to be the first test subject in this. So if you can do that, then what you can do is you can take Bruno Mars. You can then use open pose to generate not just a single image, but the actual images of Bruno Mars in each position, in each frame as he is dancing. And then you can take those poses from Bruno Mars and you can generate James dancing in the same position as Bruno Mars and then superimpose him on that. There is a video of that which I'm not allowed to show. I asked James his permission and he said it's cringe. So I'm not allowed to show that one. So I've got one with me that I will show a bit later on. So creating the source data, we're going to be basically taking a video like that, sending it through some kind of a Python script that's going to generate all of the images. You're then going to be sending the same images through OpenPose to generate all of the poses. And then you're going to be training it. So it's kind of like Pix2Pix, where instead of taking a line drawing and converting it to a photo, it's taking those actual pose image files and generating an actual person. So the network has to be trained for a specific person. You can't take, do a generic model where you can just feed in a photo of one person and generate anybody dancing depending on the photo you're in. It has to be for that specific person. And it takes about 5 days to train the model on a GPU. So I wasn't very popular at home running it's basically a gaming rig with an RTX 3090 in it. I was running it for 5 days over the summer. The thing, it's like having the hairdryer on for 5 days during the summer. When we're downstairs in the bedroom, we can still hear the thing going. Running it in Azure ML is a lot nicer because you don't have to have it present on premise. It does take a long time, as I mentioned there, to train the model. Creating the target data, you just take Bruno Mars and you basically generate the Bruno Mars poses, and then you do the transfer by taking the target poses to generate the images and then convert that into a video file. The process that's used is a GAN network, or a generative adversarial network, where we have two networks. You've got a generator and a discriminator. The generator, over time, is going to get better at producing images, and the discriminator is going to be better at telling if the images are fake or if the images are genuine. And over the timing process, both of these are trained together. The generator is then used to be able to take the input from somebody else and to be able to generate the output. So this is basically what the first image will look like. I think I can show you the training process. So these are the input images that I was using of myself, and then I converted them to the actual label images using OpenPose. So that's my positions, and the actual training process. This is kind of what the synthesized images look like. So this is starting with the first output before the network has been trained. And if I run this, you can see this is basically through every kind of training step. You can see it's got to 500 steps. I'm playing at 100 frames a second, and there's 1,000 steps. By the time it gets to 4,000 steps, the quality is increasing, and as it gets towards, say, 15,000 steps, we've got better quality. I learned so much about the training process. James was wearing, you can't even see it, it's like Darth Vader, and it says Star Wars here. There's a lot of detail in the actual T-shirt, which was it was finding really hard to pick up. And even towards the end of the training, you can't read that it says Star Wars, but you can see that it is James. And it's kind of like brewing beer. It's a big, long process. And if you get the steps wrong at the beginning, after 5 days of training, your output is going to be so-so. So you can work on increasing and getting the actual process running again. A bit about the GPUs. If you want to try this at home, tell your boss that you need an RTX 3090 graphic card. That has 24 gig of RAM. And it will take about 12 gig, I think, to load up the actual neural network. So if you don't have sufficient RAM on your GPU, then it just throws a CUDA out of memory exception. You can't go anywhere from there. You could reduce the quality of the network. If you know about network design, you could make it a bit of a simpler network. But it's really the network memory that's going to drive whether you can load the neural network. And then having 10,496 cores to actually run simultaneously, training the network is really, really nice to have on that graphic card. It actually runs incredibly fast on a 3090, faster than on some of the machines that we've got, the GPU machines we've got in Azure. I was really impressed with how quickly it runs. Unfortunately, I can't drag that box around with me and show you the training process there. Yeah, so that's what I'm running it on. If you want to train these networks, tell your boss you need one of those. Have about 64 gig of RAM because it's great to load stuff into memory. And there's going to be new graphic cards coming out, but something that's really really powerful. It does apparently play Cyberpunk 2068 or whatever pretty well on that graphic card, but I've never tried that. Yeah, so a bit about the actual results on the motion transfer, because I've not got too long left. I'll just run through the results and the actual process. So the first video I did was of myself, or was James, but then he won't allow me to show it. So this is basically me mapped onto Bruno Mars. So basically, it was a bit hit and miss. I think there should be some sound on this. Yeah. Some of the sections are better than others, and what I found is that you kind of need to be really matched on the same, exactly the same position, exactly the same frame rate. You can see that my head appears a bit bigger. Bruno Mars has different body dimensions to me, so it does get a bit confused in that his arms and torso are a bit longer. You can actually tune the actual poses to adjust them. There is a process that you can do there that will get more accurate results. Also, when the camera angle changes, it just gets completely distorted. The model is basically trained on the full position. If you give it only the top, it does actually detect the top there. But you can see it's just garbage that's coming out of the neural network here. It's not doing a good job at all of being able to classify that. So MIT, if we go back and look at their images, they were getting much nicer results on that, and they're using pretty much the same network. You can see that the quality there is a lot better. I think they even did the Bruno Mars sample that I had, which was, where is it, this one here, yeah. Yeah, the reason I used Bruno was they were also using Bruno for that. I'm going to try again and basically focus. Again, it's like brewing beer. You have to get the steps right in the beginning. You have to get the right set of training data. I was using, I think, about 20,000 images there for the actual training set. So it's quite a lengthy process to get the film, generate all of the open pose stuff before you can actually start training the network. And as I mentioned, it's a 5-day process to run through all of the training iterations to get the training processed. It's probably going to take a bit longer if you run it in Microsoft Azure, but it is also possible to do that. So the code is available on GitHub. If you do want to download that, you can go to the website. So here, they basically have the white paper. The white paper is worth reading because on GitHub, it doesn't really give you an indication of how to actually run through the full training process. It kind of says, run this command and then run this command, but doesn't really talk about, how many iterations you should do, what types of data sets you should use, how long it's going to take, and any kinds of guidelines like that, where the actual white paper does. They also use, I think it mentions it in the white paper, if I can find that. They actually use 2 frames. They use the current frame and the previous frame. And the reason that they do that is if you're just doing it on single images, the animation is going to be a bit jerky. However, if you use like the frame and the previous frame, you actually get the smoothness because it understands how the actual pose should change between two frames. And that produces a smoother result. One of the reasons why mine wasn't too great is I filmed at like 120 frames a second and the Bruno Mars is at 30 frames a second. So kind of the frame wasn't really matching. But they do talk about, I think they mention that in the paper about how they're working with this temporal coherence, I think they call it, of using the different frames when they generate the image. So definitely worth reading the white paper if you do want to check that stuff out. Okay, so on to just some final demos that I did. When I actually wrote the session proposal for this, I actually included a bit in the session proposal. This is actually me writing it and not AI writing it. I mentioned that with Alan demonstrating how a trained GAN can improve your dancing style from Andy McCluskey to Bruno Mars. One thing you maybe don't know about presenters is we don't typically build a demo and then submit a session. We submit about 5 sessions, and if one gets selected, then we have to build a demo. And then you're stuck with the problem of having to build a demo from what you promised to deliver in your session. I failed here. Does anybody know who Andy McCluskey is? Nobody. Finland's more into rock, I think, than they are into synth pop. So Andy McCluskey was and still is the lead singer of a band called Orchestral Manoeuvres in the Dark. In 1981, he became famous for his dancing style. So that's Andy McCluskey dancing, and you kind of think that that would just be an 80s thing, it would be a fad. He'd grow out of it and get on to do something else. However, 35 years later, he's still doing the same thing. And I think the most recent I could find was in, was it March of this year? He's still at it. It's a great way to keep fit, I think. You're going to break a few ornaments, but definitely going to stay healthy doing that. So my idea was, can we take Andy McCluskey and make him dance like Bruno Mars? There are some challenges that AI is not able to solve yet, and I think this is one of them. The challenge that I had really was relating to the images. What you need to be able to generate, the actual training set, is you kind of need to have a still camera. It needs to be pointing at the person. The background needs to be still as well, because the background is also going to be generated in the image. And you also need about 20,000 frames to be able to generate a model. And Andy wouldn't stand still long enough in order to be able to generate that training data, so it wasn't really possible to do that. However, we could make Bruno Mars dance like Andy McCluskey, because in the Bruno Mars video, you actually got this static background, and he's kind of standing in the same position, the background is not moving, and that basically makes for generating a fair amount of training data. So I did have a look at getting that thing running. So the first thing I did was to generate the, if I can find it, open video file and go, oh no, I've actually got that as a video rather than the actual frame. So if I go into demo vids. So the first thing to do was to basically get the training data for Bruno Mars. So I took the Bruno Mars video, and when we look at the Andy dancing, this is the Andy label that I'm going to use as the input. So that's basically captured from Andy McCluskey. You can see that it doesn't include his feet, wherever with Bruno Mars it did include his feet. Also, we kept capturing the drummer as well, occasionally appearing in it. So that was distorting things a bit. So what I had to do was to get the Bruno Mars video and then crop it. So it's kind of the same aspect ratio and the same size as the Andy McCluskey video. Then what we can do is basically do the actual training process. I didn't train that for 5 days. There wasn't really that much training data to be able to generate the full quality of the image. I think it was running for probably about 8 or 12 hours or something like that. And then we can basically map Bruno Mars across onto Andy McCluskey. So if I go into the demo videos and look here, if I go to Bruno to Andy. I haven't really pumped up the resolution much because it wasn't that great quality, but it's kind of capturing the approximate movements. I hope Bruno never sees this. Yeah, so it's sort of work, but the quality can be improved on that quite a bit. So I think that there's really impressive stuff that we've got with this generative AI. I love playing around with machine learning and stuff. I think takeaways from what I've been talking about is it's really easy to get into AI and machine learning on the Microsoft platform now. You don't have to learn Python. You don't have to learn maths. You don't have to work with all of these big data sets and GPUs. We've got the cognitive services. So using something like the computer vision, as we've seen in the previous session, for being able to work together with, say, cognitive search to do image tagging is really useful. If you want to be able to look at the actual custom vision stuff, I think my model has trained now. It is actually saying here that it's got an accuracy of 100%. I don't believe that. I think I'm using a very small amount of training images and classes, but hopefully it will understand the new bird that we have trained. So if I do a quick test, drop down to the image URL, the local files, and then need to go into the actual test data to get one that hasn't been, sorry, it wasn't that one. One that hasn't been seen before, and open that one. And you can see that's coming out with 85% certainty on that, so that seems to be fine. It does also work with music genres as well. The music genre, I trained that using PyTorch, but I've also trained it using the custom vision by actually uploading the particular mel specs. And apparently, that is blues, and that is disco. However, it's going to be really hard unless you're a professional musician to understand the difference. However, the performance on that was pretty good for just being able to do this in custom vision. So it's getting like 83%. I wasn't really using that many images, I don't think, on the inputs as well. So I was quite impressed that a custom vision service can actually do music genre classification pretty well. So this is great. This works really well. The challenge is, or the problem of the custom vision service is the cost when you start using it with video. I've got a video. I can't actually show this video. The last time I showed this when I was streaming on YouTube, YouTube basically blocked the content. The reason is that I was doing logo detection on a Formula 1 race. So I basically went to YouTube, I found like the highlights of the Hungarian Grand Prix, about a 5-minute video. I downloaded that. I then used the object detection to be able to identify certain logos in the Formula 1 race. And the idea was that, you spend millions and millions of dollars sponsoring a Formula 1 team, and, how much TV time do you get for that? And the video was basically showing how many seconds Rolex was appearing on the screen, or how many seconds Pirelli, or Shell, or these various other logos that were appearing on the screen. It did quite a nice job of being able to do that classification. Now, I think I worked out that if you wanted to do that for a Formula 1 race at 50 frames a second for 2 hours, it cost about $4,000 in actually making service calls, repeated service calls out to the computer vision service. So it does start to get expensive if you're going to be calling it multiple times. That's when it's useful to be able to understand a bit about working with PyTorch, working with Python, and working with a library. So I just basically use the YOLO 5 library for object detection. Again, that's available on GitHub. You can download it code, and you can run with it. It's fairly easy to be able to train a model. The challenging part is actually training the data sets, taking all of those images and drawing boxes around all of the Pirelli logos and all of the APS and Rolex logos on the Formula 1 race. But once you've done that, it's fairly easy to be able to train the model. Lastly, I was thinking, can I do something that's a bit relevant to the IglooConf? Going back, how many people were at the first ever IglooConf? There's quite a few were here. Dan Rosanova was speaking, and he was talking about, I think I've got his session. Yeah, he was talking about Azure messaging. So would it be possible to take this video of Dan talking about object messaging? And what I did was I basically sampled or took the actual square of Dan in that particular position doing his presentation. There's a nice lot of training data there. The challenge here is that the background is changing because the camera is moving slightly. Also, some people do occasionally walk across the background, so it does actually corrupt the training data. But Dan's kind of working with his arms quite a lot, and we can get a lot of different poses of Dan. What we can then take is this.
What is love?
So is it possible to transfer Jim Kerry's motion onto Dan Rosanova? So again, the results, because there was not that much training data, aren't that great. But I'm going to finish with this video here. Deepfake Dan, I've called it.
Hello. Thank you for having me. Thank you for being here. And I know I'm probably one of the last things standing between you and your weekend, so I'll try to be brief. My name's Dan Rosanova. I'm a program manager at Microsoft on the Azure team, and I'm responsible for a lot of the messaging services with my team that I've actually heard quite a few people talk about this week, so I'm pretty happy about that.
There you go. So I'll end with that. Excellent. So thanks for listening to the session. If you're interested in like the custom vision AI, drop onto my YouTube channel. I've got plenty of videos talking about custom vision and computer vision. And I've been reminded to mention about the URLs for the evals for day 1 and day 2. And to round off the IglooConf, I think we can all agree the cloud is the future, the cloud is the present, the cloud is everything and always will be. Thank you very much.